guys. Today I decided to make videos because there's someone who motivates me to make this kind of video and publish it on YouTube. So today I'll talk about LCA. LCA is a common algorithm used to solve tree problems. Yeah. So what is LCA? LCA is abbreviated as lowest common ancestor. So what is lowest common ancestor? Given a tree, a tree has it's a basic data structure, and here we will talk about general tree. So general tree, like if you have n nodes, so it will have the tree will have n-1 edge. Yeah. So I'll explain what is LCA. Sorry. So on a tree, so if you want to find the lowest common ancestor of two nodes, so what is lowest common ancestor of two nodes? Here, for example, like you want to find the lowest common ancestor of nodes 9 and 2. No, wait. Of nodes 9 and 10. Of nodes 9 and 10, so it will be node 2. Yeah. So, like for instance, like we want to find an ancestor, lowest common ancestor of nodes 6 and 7. So it of node 6 and 7, so it will be node 6. For example, like you want to find the lowest common ancestor of node 8 and 8, so it will be 8. Yeah. Find the lowest common ancestor of node 2 and 5, so it will be node 1. No lowest common ancestor. So why you have to find the lowest common ancestor? Because it will determine the shortest path from one node to the another node. For example, I want to find the shortest path. The shortest path leads to it's not a shortest path, it's the only path. Yeah, it's the only path that like for example, like I want to find the shortest path of nodes 9 and 7. So node 9 and 7 is, so it will be like this: 9 to 3, 3 to 2, 2 to 6, and 6 to 7. So the length is 4. Yeah, length is 4, and it passes through the lowest common ancestor. For example, like if you have a lowest common ancestor, so and the array di, which is a depth of node d of node I, like depth of node I. For example, like node 1 has depth 0 or 1. This is a root, yeah, a root of a tree. So if you are given a tree, you have to determine a root and root a tree. So its depth is 0, 1, 1, 2, 2, 2, 3, 3, 3. So so you can calculate the shortest path, like for example, like from node 9 to 7, you want to calculate the distance, so it will be d9 plus d7 and minus 2 times the LCA of 9 and 7. So here you have a path 3, d9 is 3, and d7 is 3, plus is 6, and 6 minus 2 times 1, it will be equal to 4. Yeah. So this is a shortest path from node to node on the tree. Using LCA is a common problem. Yeah, to find the distance, and it use LCA. been 5 months. Yeah, I've not upload any videos on YouTube because it due to I have to make a project, make a research on university and learn some new algorithm like this one to represent it to you guys. So there are 2 ways. No, there are many ways. Yeah, there are many ways to tackle this LCA problem. The first one is binary uplifting. Binary uplifting. Yeah. So, and this is the topic we will cover today. And the second one is use Euler Tool. Euler Tool and data structure. Euler Tool and data structure. Yeah, Euler Tool and data structure like segment tree and sparse table. Yeah. But yeah, I will discuss binary uplift because it's easier to write code and it's more straightforward than Euler Tool. They are equal. Yeah, the hardness are equal. Yeah, but I will discuss binary uplift because it relates to the HLD. It's heavy light decomposition. Yeah, it relates to heavy light decomposition. So I'll discuss the binary uplift, and and you guys can visualize it more easy. Yeah, binary uplift. So okay. If you want to find the first of all, how can you know whether a node is closer to the root than the other nodes? So there's a way to know it by using DFS. And an extra array like Tin and Tout. Tin and Tout. Okay. Tin is a time where when the DFS get into that node, and Tout is the time when the DFS get out of that node. So Tin and Tout can be easily calculated with DFS, and the time complexity will be of n. Yeah, of n. Tin, Tout. For example, like Tin of the DFS. First of all, I will call the DFS1. DFS1 is a DFS root. It's a root DFS. So the time will be like 0. This is a Tin and Tout. First of all, is 0. It's a Tin and 1, 2, 3. So it reach the leaf node. So it will exit the 9 nodes. It will be 4, 5, 6. Here, no, not yet 6, because it has to traverse all the subtree of the node 2. So it will be 6, 7, and 8, and 9, 10. Exit node 6, 11, and 12. Yeah, from this time it exit the node 2, and yeah, traverse to this node, to this subtree. So 13, 14, 15, 16, 17, 18. So you can calculate the T in and T out of the tree using the FS and with extra array. Yeah. So how can you determine whether the node is closer to the root nodes than the others? So for example, like node 2 and node 9, yeah, you closely observe. So you can closely observe. You can see that the T-in of the node 2 is smaller than node 9. It's obvious because DFS is from the root, from the root. So it will visit node 2 first and then node 9. And the T out of the node 9 is smaller than node 2. So we can write the function determine whether the node U, like use is parent. Yeah, I write it is part of node U and V, and it will return the Boolean value. Check whether the T of U, it will determine U is a parent of V, U is a parent of V, U is a parent of V. So T of U is smaller than T of V, and bitwise n, yeah. T out of U is larger than V, yeah, it's larger than V, 12 larger than 4 V, yeah. So this function will determine whether the node U is a parent of node V. Yeah, that's the first step. Yeah, yeah, bear that in mind. Yeah, and it can be easily observed. Yeah, it's easy. Yeah, DFS. Okay. First step is determine parent is parent. For me, parents node 2 is a parent of node 9. Yeah. Yeah, node 2 and node 3 is a parent of node 9. Actually, node 2 is an ancestor of node 9. Yeah, but I prefer calling it a parent. Okay. Okay. So the next step. Moving on the next step. So okay. Step 2. Step 2 is you have to use dynamic programming. Dynamic programming for the table, DB table. Yeah, you have to DB table. I'll call Dij is a ancestor of I, moving up to the power of j nodes. 2 to the power of j nodes. Yeah, ancestor of I by moving up to the power of j nodes. For example, like D9 0, so it's ancestor of 9 by moving up to the power of 0 is 1 node, so it will be the parent of 9, which is 3. Yeah, 3. Yeah, and for example, like D9 d2, oh, d1, d1, so it will be ancestor of 9 by moving up 2 to the power of 1 nodes, which is 2 nodes. 2, here it will be 2. Easily right? So yeah, okay, yeah, okay. So I'll show you how to calculate this table, dB table. Dij is ancestor of I moving up to 2 nodes. So here I'll write down here is parent dB table. So here Dij ancestor of I by moving up to the power of 3 nodes. Okay, I'll show you how to use dynamic programming to calculate this table, because when you have this table, I will show you how to find the Lca as fast as possible. Yeah. Okay, so you write the DFS. You have the DFS by inputting the U node, and the parent of U, and yeah, U node and parent of U. Okay, parents of U. You're given a tree with the adjacency list. Yeah, this is a list, ADG list G, with 1 is a root of a tree. So you can easily traverse the tree using the list G. Okay. So how to calculate DFS? Oh, how to write a function of DFS. So this is not a graph, so you don't have to have the visit array to track whether it's visited or not. So first of all, if you have PR, so you will have the dB table. The D, this is the function DFS. So you have du0 is equal to PR. PR is a parent of U. First of all, yeah, this is a parent of U. What is the parent of root node? Parent of root node itself. Yeah. So first on, I'll call the DFS 1. So the D10 is 1. Yeah. D10 is 1. D12 is 1. D13 is 1. D14 is 1. Yeah. Okay. The U0 is PR. So okay, and then I'll make a for loop. Okay, for loop for I equal to 1 to log n. Why log 2n? Why is log 2n? Why you only traverse it to log 2n? Because when you have a tree of n nodes and n-1 edge, so the maximum, yeah, the maximum height of the tree is n. So yeah, it's n. So 2 to the power of log 2n is n. Okay, so that's why it's log 2n is the maximum height value of 2 to the power of g. Okay, is it clear? Yeah. So log 2n. So next, it will be du, d for loop, and du I. What is dui? What is dui equal to? Three. Like for example, like you want to calculate d9 yeah, d9 1. For example, like you want to calculate the d9. For example, like here, you want to calculate the d9 of 5. Is it 5 or of I? For example, you want to calculate the dA, du, dui. For example, you want to calculate the dui, so you have to calculate, because you're using dynamic programming, so it will be the previous value will be pre-computed, so it will be equal to du I minus 1 minus 1 dui equal to dui minus 1 dui minus 1, is it right? Ancestor, no, no, it's not correct. It is for example, like you have this tree, you want to calculate this, then you must have this one, and it will jump to this one. Yeah, it is d90 and d91. So you want to calculate the d91, you have to know d90. Yeah. So d90 you just have to uplift it over here. So it will be du I minus 1 and I minus 1. Yeah, okay, yeah, that makes sense, right? For example, like d92, d91, it will be equal to the d of 90 and 0. Yeah. So d90 is 3, and yeah, and d30 is 2. Yeah, okay. Like you just like a to the power of n, you divide it, and it will be log n. Yeah. So we have the formula of dynamic programming here, so it's easy, right? You imagine it's jumping to the parent, and the parent jumped to the parent's parent. Yeah. So this will jump to the ancestor using the parent nodes that pre-calculate with dynamic programming. Okay, that makes sense, because yeah, we build up the solution. Yeah. du I minus 1 and I minus 1. Okay, makes sense. Okay, that makes sense. Okay, yeah, that makes sense. Okay, makes sense. And for each DFS, and the number one is just a normal transverse DFS, the DFS transverse. for u, for v in GU if PR different v, you just recall the df as VU. VU, which is V is inverse of the next node, and U, for example, like you're in DFS1, you can inverse to 2, so it will call the DFS to 1. Yeah, DFS to 1, and then it will assign the D20 to 1. So makes sense, right? Yeah, this is the DFS function, which is very important in order to build up the solution. Yeah, here's the build up step. So the time complexity to build this table is exactly n log n. Yeah, for n is a time complexity of the DFS, and yeah, and this is log 2n, so it will be n log n, exactly n log n, in order to calculate the DP table of ancestor of E up to 2 to the power of G nodes. Yeah, okay, makes sense. Okay, next, after you have this table, we'll move to step 3, which is a most interesting step, and it's a query step, which is the last step. Yeah, query. So 1, 2, 3, only 3 functions to calculate the LCA. Okay, erase it. After you have this table, Dij, yeah, you can calculate the LCA. Okay. LCA. Okay, and the next step is a querying step. Query, which is a most interesting step. UV, find the LCA. Find the LCA of U and V. How to find the LCA of U and V? By using this table. So in order for you guys to can easily understand, I will upload the source code in below the description. So yeah, it'll be easy for you guys to learn. Also, back to the problem. 1, 2, 3. 1, 2, 5. 2, 3, 5. Okay. I'll cover more three problem, three algorithm for next for upcoming videos. So how to find the LCA of U and V by using this table. For example, like you want to find the LCA of 9 and 8, yeah, LCA of 9 and 8, 9 and 8. How to find the LCA of 9 and 8? So, okay. So we will lock one node. I will lock node 8. Lock the arbitrary node. Yeah, it doesn't matter whether you lock 9 or 8. I will lock 8. Okay. So so you make a for loop for I equal to log 2n to 0 if 9 if is parent 9 and 8. For example, like u equal to 9, yeah, u equal to 9, u different parents. We'll look when node u is not a parent of node 8, and u equal to du I, okay, and then we return the LCA du0. Why? I'll explain it. First on, you log the node 8, so we'll traverse the log 2n to the 0. So what is log 2n of this node? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. So log 2 of 10 is equal to log 2 10 is equal to 4. Yeah, 4. I'll use the ceiling function, ceiling rounding function. Yeah, so we go to 4, so it will look 4 to 0. So it will look from 4 to 0. So 4, if I equal to 4, so u du 4. So u is equal to 9. So d9 4 is, it will be 2 to the power of 4, so it will be 16 up to 16 node. The ancestor up to 16 nodes of node 9, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14 to 16. So it will be node 1. It will be node 1, but one you using the is parents. 1 is an ancestor. 1 is an ancestor of node 8. So yeah, will not assign you to any number. So yeah. Next is 3. So d9 3 is d9 8. d9 up to the ancestor of node 9 up to 8 node. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So it will be, it's still 1, and 1 is still the parent of the node 8. Yeah, so d2, okay, d2, so d2, and it's equal to d9 2, which is an ancestor of node 9 up to 4 node, up to 2 to the power of 2 nodes, which is 4, d9 4, 1, 2, 3, 4, 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7. Oh, 3, 4. Okay, it's still 1. And 1 is the ancestor of node 8. So we'll not take it, and it's 1. Okay. 1, and then it will d9 1, which is an ancestor of node 9 up to 2 nodes. 1, 2 node, which is 2, and then 2 is not the ancestor of 8 by using the parent function. Yeah, 2 is not a parent of node 8. So I'll take 2. So u is equal to 2. Yeah, u is equal to 2. Yeah, and I continue the method, the loop, for loop 0 0. So 0 here, d2 0, which is a parent of node 2. So which is 1, and 1 is a parent of node 8. So 1. So u is still equal to 2. And then we look, and then it's out of the for loop, and then return to du0, which is a d20. d20 is a parent of node 2, which is 1, and 1 is the lowest common ancestor of 9 and 8. So to sum up, it's, yeah, in order to sum up, I'll describe the process. for you guys to easily to know it. Yeah. If I'll erase these things. If you have a number, like for take some number 20, not 21. Take the number 21. You look from the log n to the 0, and then you can represent the 21 with yeah. You can represent the 21 with 16, with 16, which is 2 to the power of 4. Yeah, 2 to the power of 4. Yeah, 2 to the power of 4 and plus 2 to the power of 2 plus 2 to the power of 0. 0, 2, 4. Yeah, 0, 2, 4. By transverse down, yeah, by transverse from log of n, log 2 of n to 0, you can easily take this number and add up to 21. But if you transverse from the small to the large one, from the smaller down one to the larger one, for example, like you want to transverse from 0 to log n, it will be like this. From 0 to log n, it will be 1 plus 2 plus 4 and plus 8, we did 12, 14, 15, and plus 16. Yeah, it cannot make up to 21. So yeah, it cannot make up to 21. So I'll choose the way to transverse from the larger one to the smaller one. For example, like you want to the LCA one, the LCA querying one want to find the nearest lowest common ancestor of two nodes. For example, take node 9 and 8. I want to transverse to this node, to only this node, and yeah, you can see it take path 3. It takes 2. Yeah, it takes 2 edge. For example, like I want to here. Okay, 1, 2, 3, 4, 5. For example, like this. 12, 11, 13. Yeah. Okay, for example, I want to find the lowest common ancestor of 13 and 8. So I lock 8 and I want to move to this node. So can you see the path? 1, 2, 3, 4, 5. 5. I want to represent 5 as the binary number by jumping up. Yeah, by jumping up. First on, I'll jump 4. I'll jump 4 and 1. So it will jump 4, 1, 2, 1, 2, 3, 4, 4, and jump 1. And then because on the way jumping, these nodes are not the ancestor of node 8. So you can see that I write is not ancestor, and then for the result, it only the parents of this node. Yeah, parent of this node is di0. Yeah, 2 to the power of 0 is 1. Yeah, so that's the way you find the LCA. I'll write the code. Yeah, first on you have to check whether U or V is the lowest common ancestor. So okay, so if is par UV, so if it is U is a parent of node V, so we will return U. If is par VU, so I will return V. Okay, and I'm run the for loop from log n to 0. And if its parent is u, if it's not a parent of the node log, I will choose to log node v. So if u is not a parent of v, so I'll update the u equal to u to equal to the u, right? Yeah, the ui, and then return. And when ending a for loop, you return you're standing here, which is a parent of the which is a son, which is a child of I say like discrimination between genders in gender. So it will return the du0. So okay, this is LCA problem. LCA problem. Yeah. Okay, easy, right? You only need three function to solve the LCA problem, and each function is really short. I'm not consider the building a graph using function. Yeah. So it takes three steps to build the LCA, to solve the LCA problem, and the time complexity will be I'll erase it. The time complexity of this problem, by building the B table, it will take n log n. By n log n, recompute the B table with n log n complexity, and querying will take log n, which is acceptable. Yeah. There are multiple ways to tackle this LCA problem, and the most common way is using this one, binary uplift. And the second the second common one is using Euler Tool. I'll describe generally about the Euler Tool. So what is the Euler Tool? Given this graph, you have the Euler Tool point. I'll erase this. The Euler Tool of this graph, of this tree, is first one is with 1, and then 2, 3, 9, 1, 2, 3, 9, and then it back to 9. It takes 9 and it get back to 9. Yeah, 9 and 3, 2, 6, 10, 6, 7. Oh, you can get this value. It doesn't important. Yeah. 1, 2, 3, 9. Get back to 3, 2, 6, 10, 6, 7, 6, 2, 1, and yeah. By finishing this subtree, you traverse the next subtree using this method. It will be 1 and 4, 8, 4, 1, 5, 1. Okay, that's the Euler Tool. And by using Euler Tool, you have this node, and you will I don't know how to say this word in English, but it will answer. Yeah, it answer the the nodes to the index of on array, and using the array, using the array, and you have the height of each node, and you write the height of each node here. And then whenever you want to find LCA of for example like 9 and 8, you take the query from 9 to 8. You find the minimum height of this subset, this subset, and yeah, the minimum height. So the minimum height is 1, and 1 is the LCA of 9 and 8. Yeah, because there's on a Euler Tool path. On a Euler Tool path, yeah, on a Euler Tool path there consists the lowest common ancestor nodes. Yeah. So by tackle on a range query, you're using sparse table, and or segment tree. The sparse table built at log n time and query for each minimum time. For minimum, querying for minimum is constant time, and segment tree is n log n. Segment tree for build is O n, and for query is log n. But due to high constants, we recommend using sparse table. There's a way to optimize the sparse table to O n, recompute the table, and constant time for querying the value. But here we discuss the binary uplifting method to tackle the FCA problem. Thanks for watching.